All right, everybody, let's get started today with the problem of the day that you had to work on over the weekend. The problem of the day was looking at a mass spec problem where it said that we have 5 different constitutional isomers for C4H8. So your first task was to determine all of those different isomers. The key thing that you should have noticed is that they needed some sort of double bond or ring in them. So there's an internal double bond or an exterior double bond. Alternatively, you can have this isomer, or you can have cyclobutane, or you can have methyl cyclopropane, which is another isomer. So all of these either have one pi bond in them or one ring in them, and those limited your options a little bit. So in the instructions, it said that there was a really strong signal at a mass to charge ratio of 41, which means we lost how much mass from our parent ion? We lost 15, which corresponds to a methyl ion. So if we look at this, we can circle a methyl radical that could pop off from each of these. And we could say, all right, that one could pop off, this one could pop off, this one could pop off. What about with cyclobutane? Nope, we could lose 14 theoretically, but even then, it's probably not going to be super likely. So we know it's probably not going to be that one. And then with methyl cyclopropane, we could lose a methyl radical right there. So let's take a look at each of these radicals. And so for the first one, we've got this radical. Is there anything that can stabilize it? Yeah, resonance, right? So if we look at that, we can say, all right, we can move the double bond over here, and it's resonance stabilized for radical 1. What about the second radical? Is there any resonance there? What do you guys think? No, exactly. So this was something that hung up a lot of people. What I'm going to do is draw in all of the hydrogens, and you guys should be able to see that there's no resonance with a vinylic carbocation. The hydrogen down there. Let me move this over a bit. We can try to push these electrons over. Let me grab my pen. If we move these electrons over there, we're going to violate the octet rule, and we know this is not allowed. I'll draw it out anyways just to prove a point. Oops. Shoot, I'm messing up my resonance structure that I was trying to do because it doesn't work. Let me redraw this really quickly. This isn't a very good resonance structure, is it? So if we look at this one, we have to ask ourselves which one's going to be the most possible or most probable constitutional isomer. Is it going to be the one on the left, the middle two, or the cyclopropane? What do you guys think? Yeah, probably going to be that one on the left, simply because it's stabilized via resonance. If we look at the other carbocations that we would get out, they're really not going to be that stable. The first isomer that I have drawn is going to be the most stable one. One other thing that people were getting kind of hosed up on was they also were drawing isomers that looked like that. Is that another constitutional isomer? How is it related to the one on the left? Yeah, they're diastereomers, not constitutional isomers. So constitutional isomers have to have completely different connectivity. So in this case, mass spec is somewhat useful for determining structures of constitutional isomers, but it can't distinguish very well between diastereomers. So we are kind of limited with what we can do with mass spec. But what we're going to do is we're going to learn some new tools that can be used to distinguish between diastereomers and a lot of other structural features within molecules. So let's finish up our mass spec portion. And last Thursday we talked about analyzing our mass peak, that parent peak, which gives us the weight of our molecule, which is very important. Then we went on to say we can examine that mass plus 1 peak, which we can use to determine the number of carbons. And then conversely, we can look at the mass plus 2 peak to look at whether or not there are halogens in it there, and whether or not that halogen is a chlorine or a bromine. But there's some other really useful features, which you guys saw, and those are mass fragments. And the key with mass fragments is that some carbocations show up more intensely. Show up more intensely. The way I was describing it to somebody earlier is it's kind of like a bomb going off in a parking lot, right? I know it's a kind of a destructive example, but it will blow up a bunch of cars just like a mass spec blows up a lot of individual molecules. And what we're looking for is the chunks that were the most stable. That means they were the most rugged part of the car, right? So we might see a lot of car frames. We're probably not going to see a lot of glass, right? So it's the same idea with the mass spec. We're taking a bunch of molecules, bombarding them with electrons, and then trying to find the most stable fragments that are the result of that. So there's a higher probability of observing stable fragments. There's a couple different things that can stabilize these carbocations. The first one is hyperconjugation. So if we think back to first term and we talked about the stability of carbocations, we said that tertiary carbocations are more stable than secondary carbocations. These are much more stable than primary carbocation, and these are much, much more stable than a methyl carbocation. So we can look at our mass fragments and kind of deduce what a lot of the fragments are based on the intensity that they show up at and the amount of mass that was lost from the parent mass. It's not uncommon to see a tert-butyl group get blown off because we form a really stable tert-butyl carbocation. So anytime you see something like that, that can be a good hint. The next thing that we saw in our problem of the day is resonance. And with resonance, there's a couple different ones that show up really well. The one we saw in our problem of the day were allylic carbocations. So if we've got something like the molecule that we showed, it can quickly decompose from its parent radical cation into a stabilized allylic carbocation that we know is resonance stabilized. And we can eject off some sort of, in this case, a methyl radical, but really any sort of alkyl radical. It's important to remember that when we're looking at mass specs, or mass spectra, that we're only looking at carbocations. That's the only thing we can observe. The radicals are silent in mass spec, so we won't see the methyl radical, we'll only see the allyl cation. The next one that shows up really well are alcohols. So if we think about an alcohol, I'm going to draw it in a very special way. When we bombard this alcohol with electrons, the first electrons to get dislodged aren't bonding electrons, they're actually lone pair electrons. So if we look at this, we're going to knock off one of these electrons on the oxygen, giving it a positive charge. So we've got our radical cation. And then we're going to name these positions. So the position where the alcohol is attached will be called our alpha position. The next one over will be our beta position. What will happen is these will quickly rearrange. This radical will jump down. It'll take one electron from this other bond. Let me draw that more clearly. And then the other electron from that bond will jump over to the beta carbon. And so now if we do that, our oxygen still has a positive charge, but the really nice thing with this is that it's resonance stabilized. So we can draw it out where that positive charge is delocalized. So that's the carbocation fragment. Just like with our allyl-cation, we observe the cation. And then the other fragment that came off, in this case, is going to be our ethyl radical. So that beta proton, if we look at where it is, it's now over here. And our alpha proton is over here. So that alpha proton can delocalize, or that alpha position can delocalize that positive charge, and the beta position can become a radical. Oftentimes, alcohols undergo further degradation. We'll cover that next. But oftentimes, alcohols, when you observe them in mass spec, have really strong peaks because when you pop off some sort of radical off of it, you've got a really nice stable cation that's stabilized through resonance. The same thing can be said for amines. So if we've got an amine, we can still have this alpha and beta position. Oop, I drew too many electrons. And so this should be our radical cation. We've ejected one of those electrons from the nitrogen, giving it a positive charge. And now this radical can hop down. This electron from that alpha-beta bond can hop over, and then we can eject off a new radical. So we still have our amine on there, but now we've got a double bond to our nitrogen, giving it a positive charge. This can delocalize where this pi bond can hop up to the nitrogen. And just like with the alcohol, we've moved that positive charge over to the alpha position. And in this case, we've ejected an ethyl radical. So these carbocation fragments show up really, really well just simply because they're stabilized through resonance. So hyperconjugation and resonance, we've already seen these in terms of carbocation stability. We just haven't seen alpha cleavage in terms of mass spec or using radical reactions. Does that make sense?
So you have two beta carbons there.
Yeah, in this case, I just chose one of them. You could have fragmented either of those. Yep. That's a good question. All right, there are some other really useful tricks for analyzing these fragments. Specifically, we can just look at weights. So I'm going to call these quick clues. So if we've got our mass minus 15, we saw this in our problem of the day. What did that mean we lost? Yeah, so loss of a methyl radical. What about mass minus 29? What would that probably be? Yeah, loss of an ethyl group. We can keep on going and we could say mass minus 43 and mass minus 57, and these would be loss of a propyl and then loss of a butyl. So these are really quick clues that we're starting to break down our long alkyl chains. There are some other really useful ones, and we're going to cover these. Mass minus 18. What's something that might weigh 18? Water. Exactly. So loss of water is frequently observed. And I'm going to put in here alcohol. And we'll see what I mean by that here in a second. The other one I'll put is mass minus X. And I'm going to label this with an asterisk, where x equals an even number. And what this is it's called a McLafferty rearrangement. And this is really indicative of an aldehyde or a ketone. All right, so let's kind of address these last two because we haven't really seen a rearrangement where we observe loss of water or a rearrangement of a ketone or aldehyde. So I'm going to box this off. And let's first look at the loss of water. And we said that if it's losing some sort of water molecule, that means it's probably coming from an alcohol. But let's see the mechanism. Let's say we've got this alcohol here. And we've bombarded it with electrons, knocking one of those electrons off the oxygen. Now this oxygen's got a positive charge. But if we look over towards that oxygen's right, there's actually a proton hanging out. So I'm going to draw this proton as blue. What will happen is we'll get a really quick rearrangement. This will take one electron. This will pop over, and then we're going to move both electrons up to this oxygen. So it's a very unusual rearrangement that involves movement of not only single electrons as radicals, but a set of electrons too. So that oxygen-carbon bond, we're moving both electrons. And if we look at what's going on here, we're going to eject off this water molecule, and it will have 2 electrons on that oxygen. And then we're going to form a new radical, specifically a new radical cation. So there will be a cation in the position where the carbon was, and then we'll form a radical over here. So it's pretty common anytime you have an alcohol to observe a loss of a water peak. The hydrogen doesn't have to be in this exact position, but in proximity, and you can actually have a hydrogen get transferred over to that hydroxyl group. That water will pop off and leave you with a radical cation as a new strong fragment peak. You have a question, Kareem? It needs to be at least in, let's actually go over this. If we look at this, this is alpha, this is beta. What's the next position? Gamma. It needs to at least be in that gamma position. It can be even further though. Occasionally you'll even see it where it's across different molecules, but that's pretty rare. Yeah, it needs to be gamma or at least one further away. Typically molecules like to go through 6 membered ring transition states, so those tend to be the most common.
So at least 2 carbons away.
Yep. The next one is that McLafferty rearrangement. And this is for aldehydes and ketones. And so let's draw out an aldehyde here. Actually, I'll just label one side as R. That way we're not calling it just an aldehyde or just a ketone. And so when we shoot this molecule with electrons, we're going to knock one electron off of the oxygen, giving it a positive charge. Right? So now we've got our parent molecular radical cation. If we do this, we again have those alpha, beta, and gamma positions. So we've got alpha over here, we've got beta over here, we've got gamma over here. What I'm going to do is I'm going to actually draw this a little bit differently. In this case with ketones, it's actually one carbon over. Yeah. So let's draw it a little bit differently. So I'm going to label this alpha, beta, gamma. And in this gamma position, we also have a proton nearby, right? Just like I said, these really like to form six-membered transition states. So we've got a proton that could form a six-membered ring. So what will happen is this radical will hop over, grab an electron from that bond. Another one will hop over here. Oh, that shouldn't be a double-headed arrow, single head. This bond between the alpha-beta position will also get cleaved homolytically. And I know it's a lot of arrows, but what we're doing is we're forming a new bond between that beta-gamma position, and we're putting a single electron onto the alpha position, and then we're forming a new covalent bond between that oxygen and proton. So let's draw out the product that we get. So if we look at it now, that beta-gamma position is going to be a double bond, so I'm just going to label this beta and gamma. Even though they're no longer in that beta-gamma position, I just want to keep track of the carbons. And then we will also get the other fragment where there's a radical on that alpha position. And then we'll also have a new covalent bond over here. Question is, why would it want to rearrange into this carbocation? Is this a stable carbocation? Kinda. So let me actually redraw this lone pair a little bit better, and we'll see if there's any resonance structures for it. So we can take this single electron, dump it down there, an electron from there, dump it down, and then a single electron and dump it up. So if we do this, we now have a new double bond. We've got a single bond from that carbon to oxygen. Now the carbocation is on the oxygen. So the reason, forgot my R group. The reason that this carbocation is so stable is because we've got resonance delocalization on it. So McLafferty rearrangement, if you look at it, we're always ejecting off a piece that has some even mass on it. So when I had that chart up here, I said that oftentimes when you see a mass minus some sort of even peak, it often means that you're ejecting some sort of alkene. Even, whoa, not even. And this is kind of unique because if we look at our chart, if we're losing some sort of alkyl chunk, it's normally coming off in an odd number. But with the McLafferty rearrangement, we're actually losing some even weight fragment. So this is kind of like doing detective work. It's not immediately clear when you first get your mass spec what's going on, but you have to break it apart using kind of the system that we've covered in lecture. So let's quickly go through our guidelines for interpreting mass spec and try to come up with some sort of systematic scheme of breaking down all the data that we have, because I know it can be really overwhelming when you see it all at first. All right, so the step number one is pretty easy. We want to just determine the molecular weight. How can we determine the molecular weight of our molecule of interest? which peak will tell us? It's going to not necessarily be the highest one, but it's going to be the most intense one in that highest fragmentation peak. So it's going to be that parent radical cation peak. So it's going to be the most intense peak furthest to the right. The second thing we can do is look at the peak that's just right above it. And this will determine the number of carbons. So that's another really useful clue we can get from the mass spec. So now we've got the molecular weight, we've got the number of carbons. The third thing we can do is look for a M+2 peak, which tells us what? Yeah, it tells us halogens, right? So halogens oftentimes have an isotope that's got an additional 2 neutrons. So determine if halogens are present. From our M+2 radical cation. Our fourth thing is we want to analyze our fragments. And the reason we really want to look at these fragments is it can give us clues that maybe there's an alcohol, maybe there's an aldehyde, maybe there's an allyl fragment in there. So we want to look for evidence of those things. Evidence of amines, alcohols, etc. So you can use that table that we just came up with to look at some of our fragments, figure out what they are. The fifth thing you want to do is try to determine the molecular formula. So now we've got some really useful information. So the first thing we start with is our number of carbons. We can figure out if there's an oxygen. Usually like an alcohol will have that loss of water peak. We can determine number of nitrogens. How will we know if there's an odd number of nitrogens in there?
It's an
Odd molecular weight, right? So we can pick up a lot of these clues, try to piece together a molecular formula. Oftentimes it's not super clear, but you have to troubleshoot and try to deduce what you think the molecular formula is. And then number 6 is really useful. And this is determine the hydrogen deficiency index. And the book calls this the HDI. I think Sapling has some other acronym that they use for this. It still is referring to the same thing. And what this is useful for is it can tell you the number of pi bonds or rings in your system. So there's a special formula for it that's equal to 1/2 times double your number of carbons plus 2 plus n minus h, which is your hydrogens, minus your number of halogens. And this will tell you your pi bonds plus rings. So for example, if you went through and you tried to do the hydrogen deficiency index for C4H8 on our problem of the day, what should it be? Let's even try to do this. So we'll do C4H8. We know that it will be 1/2 2 times 4 plus 2. What about our nitrogens? Don't have any, so we'll just say 0. Minus 8 minus 0. So 2 times 4 is 8. Plus 2 would be 10. Minus 8 would be 2. 1/2 times 2 equals 1, right? So if we look at this, 1 means we have one ring or one pi bond. Right, so if you think back to the isomers we drew, we had 2 of them that were rings and then 3 of them that had pi bonds. So this is actually a really useful tool that you can use once you have your molecular formula to determine some sort of structural information. Yep?
This works for any structure?
Works for any of them. Yep, and you don't have to memorize this formula. I'll give it to you on exams and quizzes. It's not worth memorizing. Just know how to use it if I give it to you. All right. The 7th thing is just to narrow down your structural possibilities. Stabilities. Mass spec is really useful for a lot of things. If you watch CSI, they make it sound like it's this savior of chemistry. It will tell you any molecule that you have very conclusively. The reality is it tells us a lot of information, but it doesn't tell us the complete story. If we're looking at things like diastereomers, it won't tell us which diastereomer we have. If we're looking at enantiomers, it'll tell you the molecular weight of the enantiomer, but you won't know whether or not it's R or S. So mass spec is somewhat limited in its usefulness. It tells you a lot of information, but it's just one tool that chemists have at their disposal. Typically, when chemists make a new compound, they have to go through essentially a publication procedure where they prove to other scientists that they made that compound. They have to prove beyond a reasonable doubt that they did. So oftentimes when you pull up a chemistry publication, they'll give you an IR, they'll give you a mass spec, and then they'll give you something called an NMR, which is what we'll cover next. And those 3 things together are usually enough evidence to convince other chemists around the world that you made what you think you made. If they have problems with it, they'll chomp at the bit to prove you wrong. That's how chemists oftentimes work. They can be a little brutal sometimes. All right, so let's switch gears to NMR. NMR is a little bit more abstract than mass spec or IR, but I'll do my best to explain it in a pretty reasonable way. So NMR stands for Nuclear Magnetic Resonance Spectroscopy. Has anybody ever known somebody that's gone in for an MRI? Yeah, a lot of people probably. MRI is the exact same concept. They don't call it nuclear magnetic resonance imaging because that freaks people out. They think they're being exposed to radiation. The reality is they just trimmed off the nuclear part because it got people a little antsy when they went to the hospital. Same sort of concept, except we're not doing it on entire people or animals. We're just doing it on single molecules. And the interesting thing with this is that atoms actually have a quantum property called a nuclear spin, specifically if they have an odd number of protons or neutrons.
Are you going to demonstrate? Our last teacher demonstrated the spins for us.
I'm going to do my best. I've got some videos that I'll show you too. So atoms are nuclei with an odd number of electrons, or sorry, protons or neutrons. Have nuclear spin. And the way I imagine this is, I'm going to move this over to the side. Let's say we've got a proton here with a positive charge. This positive charge will essentially spin like a top. So I'm just going to draw it spinning that way, right? Almost like a little top. I don't really have it drawn that circular, but you get the drift. If we're spinning it this direction, we're actually going to generate a magnetic field, right? Anytime you spin a charge, you get a magnetic field. If you've taken basic physics, you guys have probably covered this in electromagnetic, or in E&M. If you do this, you end up getting these magnetic fields kind of forming a ring around your atom or your nucleus. So the spinning charge is almost like a little magnet where we've got a north pole on the top side and we've got a south pole down here. In solution, these will all be pointed in random states. We'll be pointing in different directions, so that magnetic direction won't be uniform. It'll just be completely random according to population distributions. But let's take a look at this app. I've got the app on here. You guys are welcome to pull it up at home if you'd like to. But I think it does a nice job of explaining how the spectrometer actually works. So let's say we do have this north and south pole. We can think of it like a compass, right? So I've got this compass over here. What we can do is try to align these magnets using a bigger magnet, right? So opposites attract, like charges repel. So what I'm going to do is I'm going to bring down a really strong magnet, and I'm going to align all of my nuclear spins so that they are aligned in the same magnetic field as this bigger magnet. And you can see that the nucleus actually takes a while. It acts like a pendulum, and then it slowly relaxes into that magnetic field. Oftentimes, the magnets that we use fall into two classes. They're either big permanent magnets or they're superconducting magnets. The NMR that we have upstairs is a permanent magnet. If you go to a university, they use superconducting magnets usually. And these need to be constantly cooled with liquid helium, which is a big problem right now because there's actually a liquid helium shortage in the US. But that's a different story. So now we've got all of our nuclei aligned along an axis, right? So what we can do is we can try to knock it off axis. So what we do is we can take another little magnet and shove it up against there, right? So I tilted it a little bit off axis. It's not very far off axis though, right? What if I do it over and over again? It's kind of like pushing a kid on a swing. If you push too fast, it won't work very well. But if you hit it at the right frequency, you can actually get a nucleus to start spinning really far off axis, so far that it actually hits 90 degrees. Kind of like pushing a kid all the way up to 90 degrees. They get pretty excited if you do that. So let's crank this up and then do the frequency. And you can see that a lot of little pushes will get this very far off axis. That frequency where you start getting it really off axis is called its resonance frequency, right? So we're hitting it at a certain frequency that corresponds to knocking that nucleus really, really far off axis. And this is very, very useful. And so what happens, I'm going to stop this here, is we start knocking this top off axis. So you can think of it like a top spinning all oblong, and then it wants to relax back into that big magnetic field right above it. So imagine this rod is our sum of vectors. It will actually spiral back into the plane of that parent magnetic field, right? So just like a top going right back into the up-down position, it'll try to relax back into there. So that's essentially how it works. If we look at it, this magnet that's going perpendicular to the big magnet is actually electromagnetic radiation from radio waves. So we can take radio waves, we can pulse frequencies of radio waves at a nucleus that's aligned in a magnetic field and start to perturb it off axis and try to find the resonance frequency at which the nuclei gets perturbed off axis. Does that make sense? It's a little abstract. It's a lot of physics. Really what I'm going to be most interested in is you guys being able to interpret NMR spectra, but we've got to cover some of these basics first. So I put the magnetic resonance app and, the other app in the class notebook, so you're welcome to observe those. But really the key take-home message is that we align nuclei in a magnetic field and then a second perpendicular magnetic field is applied. And I'm going to say radio waves just so we're being specific. To knock the spin off axis. And then afterwards, the nuclei relax back into the magnetic field. And we can actually detect how it's relaxing back into that magnetic field. So when it relaxes, it actually emits energy back out that we can detect pretty easily. So the spectrum that we get is actually something that looks a little bit weird. We've got time on one axis, and then we've got induced voltage. And induced voltage is just the energy that we're detecting out. So when we knock it off axis, it's going to start vibrating like that, right? It's not a very useful spectrum, right? It just looks like a bunch of squiggly lines to me and everybody else on the planet. What this is called is a free induction decay. So just like any good scientist, when you get data that looks really complicated and messy, what do? You go ask a mathematician to make it look nicer. And so we can actually do Fourier transformations of this data to make it look much, much nicer. And we're going to cover what we can do to this in order to interpret it much more usefully. But the first step that we need to do is actually look at our spectra, or our compound of interest, and look at the number of signals that we should anticipate in our spectrum. And so I'm going to kind of guide you guys through this. And then we'll go back into the nitty-gritty of what's going on in our spectra. So the first thing is that nuclei in the same chemical environment have the same resonance frequency. And if you remember, resonance frequency was how often do we have to knock that nuclei off axis to get it really off kilter. And that's the resonance frequency. If you're in the exact same chemical environment, it takes that exact same frequency to knock another atom off axis to that same degree, or another nucleus. So let's take a look at an example molecule here. I'm going to take dichloromethane. And specifically, the nucleus that I want you to look at are the protons. So I'm going to label this proton A and this proton B. Are they in the same chemical environment, or are they in different environments? This is a little bit abstract to think about, but we're going to do a little mental exercise here. Imagine that you are the proton, right? Right? It's pretty deep. But imagine you're this proton and you're sticking up in that HA position. And you're looking around and you look down and you're saying, all right, there's two chlorines in front of me. There's a proton behind me. So essentially, I look down, I see two chlorine atoms and a proton. What about if you're HB? Imagine that you're the proton in the HB position. If you look down, do you see anything different? No, exactly. So we can do this with our model kits too. So what I'm going to do is take out these two protons, HA and HB. So now I've got two of the same molecules. This HA one is pointed up. Let's see if we can get HB in that exact same position. Right? They're in the exact same chemical environment. And so when I'm talking about chemical environment, just imagine that you're the atom in that position. Are you in the same position or a different position than the other protons in that molecule? And HB in the same environment. All right, let's do another one. This time what I'm going to do is I'm going to look at an ether. So this is dimethyl ether. And what I'm going to do is I'm going to make a really quick model of what's going on here. Sorry, this will take me just 1 second. All right, so let's get our model kit for dimethyl ether here. So this center vertex is going to be oxygen. The outer are going to be our methyl groups, right? So if I look at these protons on the methyl group, are they in the same or different chemical environment?
No.
Kind of a trick question, right? So if we look at this proton up here, it's closer to the oxygen than these ones down here. But do molecules sit still in space? What's actually going on? These sigma bonds like to spin around, right? So if we're thinking about this as a helicopter rotor, are they in the same chemical space? Yeah, exactly. So we also have to think about sigma bond rotation because that can actually influence chemical space here. So if we look at these ones down here, we can say that all of these protons in all of these positions are essentially in the same chemical space. Why are the ones on the right the same as the ones on the left? Yeah, it's symmetry, right? If we're spinning them around, they can't really determine if they're in the same position or a different position than the ones on the left. They're in the exact same chemical environment. So all HAs are in the same environment. All right, let's quickly mention the obvious thing is that if nuclei are in a different chemical environment, that they have different chemical or resonance frequencies.
What was resonance frequency again?
Resonance frequency is, imagine pushing a kid on a swing. If you go up to a kid and you go, they're not going to start swinging, right? If you're just bashing them. But if you do nice slow pushes, you can actually hit their resonance frequency on the swing and get them pushing really far off axis. You just have to be pushing them at that right frequency. Essentially, that's what a resonance frequency is for a spinning charge, too.
After they've been lined up.
Mm-hmm. So after they've all been aligned in that same magnetic field, what sort of frequency do you have to push them at in order to get them to start going off axis? Have different resonance frequencies. All right, with the problem of the day, hang on to it. You don't need to hand it in tomorrow. We'll actually work through it in class together because I don't think we've had enough time to really practice this. So just bring it with you in class tomorrow and we'll use it as a guided activity that we'll work on together. All right, I'll see those of you who have Monday lab in lab.